let's look at asymptotes in a little bit more detail. So when we're drawing our sketches, we know curves will always bend towards the asymptote. We saw that they will never cut a vertical asymptote, but they can cut horizontal oblique, because that's telling us what happens out at infinity. Now, if we've got a function which is basically a rational function, so you've got some fraction, you've got a polynomial on the top, polynomial on the bottom, you could do a polynomial division and you'll come up with something like that, the quotient plus the remainder over the divisor. When you've got it in that form, that tells you a heck of a lot about the graph. The bottom of the fraction, as we know, we'll find our vertical asymptotes. So we can solve that. The quotient turns out to be the horizontal or the oblique asymptote, depending on what that function turns out to be. Then the top of the fraction will tell you whether or not it cuts that horizontal or oblique asymptote. So you solve the top of the fraction equaling 0, and if you get a solution, you know that's where it will cut the horizontal or oblique asymptote. So let's use this as an example. So I've got it in factorised form at this stage. Now, if I was to do a polynomial division, the bottom of the fraction, you'll notice, is different to 2 squares. So I'm dividing by x squared minus 1. The top turns out to be x squared plus x minus 6. So x squared and x squared goes once. That leaves me with a remainder of x minus 5, and that's where I have to stop, because x squared won't go into x. So I know I can rewrite that function as 1 plus x minus 5 on x minus 1, x plus 1. So let's find the information. X-intercepts. I go back to the original one for that, because we want to know when does the function equal 0. That's when the numerator equals 0. We've got minus 3 and 2. Plot those. Okay, the y-intercept, that's always easy to find. Substitute in x equals 0, and I get 6. Vertical asymptotes. Bottom of the fraction can't equal 0. So plus or minus 1, we've got vertical asymptotes. Let's dot those in. We know we have a horizontal one at 1. Let's draw that one in. Okay. Now, can it cut that asymptote? Well, if I solve x minus 5 equals 0, I get x equals 5. So yes, it will cut at the point 5, 1. So all right, that should be enough to get a pretty good sketch. It's got to go through those points I've plotted. It's got to bend towards the asymptotes. So if I start at the left, I must be in the bottom half of it, because I've got to go through this x-intercept. So I know it's going to do that bit. Now, in between these two asymptotes, it's got to go through the point 6. But it must be an upwards U, because it doesn't cut the horizontal asymptote there. So it can't go down. So I know, right, in between it must do something like that. Now, what on earth is happening on the right-hand side? It's got to go through this x-intercept. So it must start down here, because if it started up the top, it can't cut the horizontal asymptote in order to get to 2. So it must start down the bottom. It goes through 2, it then must go through 5, but it's got to bend towards the asymptote. So some point after x equals 5, it must turn around, come back down, and turn towards the asymptote. Well, mine's a little bit dodgy there, but you get the idea. It's got to come through, bend, and come back down. Let's have a look at this one. So x minus 2, x minus 1, x plus 1 on x plus 2, x minus 3. All right, polynomial division, we'll do it again. This time I've got a quadratic into a cubic. So x squared into x cubed goes x times. That leaves me with minus x squared plus 5x plus 2. I can keep going. X squared will go into that. So x squared into minus x squared minus 1. That leaves me with a remainder of 4x minus 4. That's as far as I can go. X squared won't go into 4x. Okay, so we know that this fraction can be rewritten as x minus 1 plus 4x minus 4 over x plus 2, x minus 3. Let's get all our information. X-intercepts, go back to the original one, which has already been factorised for us, saves us some time. So we've got x equals 2, x equals 1, and x equals minus 1. Plot those in. Okay, y-intercept, substitute in 0, we get negative 1/3. Vertical asymptotes, bottom of the fraction can't equal 0. So we will get minus 2 and positive 3. All right. Now this time we don't have a horizontal asymptote, we've got an oblique one. It'll be y equals x minus 1. Let's draw that in. Well, normally now I'd say does it cut that asymptote? But I can see already that it does, because we're actually going through our x-intercept, that line. But just to confirm, oh yeah, look, solve 4x minus 4 equals 0, and indeed you get x equals 1. So it confirms what we already knew. All right, so what is our curve doing? Start at the left. Haven't got any points. It's either going to be stuck in this little triangle down the bottom, or it'll go above and come down, but I don't have an x-intercept. So I must be stuck in the triangle down the bottom here. Oop, in there. Now, in between these two, remember, as far as we're concerned, between these two vertical asymptotes, it's like this diagonal green line doesn't exist. Because the diagonal green line is just telling us what happens out at infinity. And that's why it doesn't matter whether we cut it. All right, we start where? We're either going to start up here at positive infinity or down here at negative infinity. But I've got to get to negative 1. So I've got to start up here, because we know it doesn't pass through this one. So I'm going to start up the top, come down to negative 1, it's got to go through minus a third, it's got to go through 1, it's got to go through 2, so somewhere it's going to turn and come back down, and then it must end up back down there. Whee! There we go. Something like that. And then the last bit, the right hand side. I'm either stuck in the triangle at the top, or I'll be coming down the bottom, but again, we don't have another x-intercept, so I must be stuck in the triangle at the top. Voila! There's our sketch. So all that information we got by just looking at the equation itself and rewriting it in a format which made it easy to read the information off. That brings us to graphs of reciprocal functions. So when we want to turn a function upside down, if you know what the function is, the original function, it makes life a lot easier. Things we know. Well, if I turn function x upside down, well, when function x is equal to 0, turn it upside down, I must end up with a vertical asymptote, because now it's going to be undefined. Can't have 0 on the bottom of a fraction. Here's random curve. And on random curve, I tried to draw in every feature I could think of. I've got a horizontal asymptote there, vertical. I've got asymptotes going to the left, right down. So hopefully we've got everything here. So what did I just say? I said where the original curve is equal to 0, the reciprocal will be undefined, or a vertical asymptote. So looking at my graph, I know my new graph will have vertical asymptotes in those 3 spots. What else do I know? Where the original graph, where its y values were going towards infinity, or minus infinity, then the reciprocal must be going towards 0. So vertical asymptotes on the original graph will become x-intercepts, sort of. All right, so my vertical asymptote will become an x-intercept, sort of. You'll notice I've plotted in a hollow circle. Because, you remember yesterday I did the y equals x on x, and it looked like y equals 1, but we had the circle drawn because the bottom of the fraction. Same deal here. So because I'm drawing 1 on function x, well, I can't magically put that in the domain now. It wasn't in the domain of function x, so it can't be in the domain of its reciprocal. So I put a hollow circle there. Now, those 3 points are really easy. If you work out where the y values are equal to 1, because if you turn 1 upside down, you get... So that must be where my new curve will intersect my old curve, because they're both going to have a y value of 1. You could do the same with negative 1. If you turn negative 1 upside down, you'll get negative 1. So let's plot that one in. And, well, my diagram's out a little bit. Let's pretend that turning point there's at negative 1. Horizontal asymptote. I've put the new one in up here. How do I work that out? This horizontal asymptote is totally random. I don't know what the number is. But I do know that the y value of this horizontal asymptote, the original one, is less than 1. You turn a number less than 1 upside down, you're going to get a number that's bigger than 1. So the new horizontal asymptote must be above 1 somewhere. I'm just guessing where it is. I just know it's above 1 somewhere. Where the original graph is increasing, so the original graph is going up, The new graph, turn it upside down, it'll be going down. And vice versa. The sign won't change. Where the original graph is positive, the reciprocal graph will still be positive. And vice versa. So if I look at this one, what I'm doing is I'm just shading in all the areas I know where the curve will exist. Working from left to right. Look at the original graph. The original graph is below 1, but above the horizontal asymptote. So when I turn it upside down, the new graph should be above 1 and below the horizontal asymptote. So I know it must be somewhere in that rectangle. Okay, next piece. Between the red dot here and the asymptote, my curve is above 1 and it goes off to infinity. Turn it upside down, it must be below 1 and going off to 0. All right, next section. My original graph is below -1, so therefore my new one must be above -1. And again, it's heading towards infinity, so turn it upside down, it'll head towards 0. Next section, this tiny little bit in here. This tiny little bit, it's above my -1. Flip it, it goes below. Next bit, the original graph is below 1. Flip it, above 1. And so on, and so on, and so on. So I can work out all the sections this new graph will be in. Now, we haven't done calculus yet, so you're just going to have to take my word on this one. If I was to differentiate 1 on function x, I will end up with minus the derivative on the function squared. That's telling me then the original stationary points, and we will find this out later, do not panic. Stationary points occur when the derivative is equal to 0. So when I turn it upside down, my new derivative still has the derivative of the old function on the top. If that's equal to 0, this new one's got to be 0 too. That's a technical way of basically saying those turning points have got to stay as turning points. They won't change. The y values might change, but the actual x value of those turning points won't change. All right, so let's plot that point in. Here's a turning point. It's above 1, so its y value will become below 1, but I know the curve will turn there. The other turning point, well, remember I said it was on -1, so it's going to stay at -1. I think I've got enough information to draw a graph now. There it is. Y equals 1 on function x. Now remember, my random graph that I've drawn here, I've tried to get in as many features as possible. I think you'll find in the exercise, they're not going to have everything in the one graph. It'll just be, oh, okay, how do I turn this one upside down? And so on. Whoop, there it is. Take away the old one. What a lovely looking graph. All right, see how we go with some of those. 5C.